Alright, welcome back. In this video we're going to wrap up our unit on integration techniques with complete the square. So if you look at this list of techniques of integration from the AP Calculus course description, you'll see some of these we already did like last semester. Like antiderivatives that follow directly from derivative rules. We did use substitution. We did a little bit of rearranging first, like distributive properties, stuff like that. We did that when we were studying calculus AB. Okay, then we came back and we did product integrals. We learned about UDV, integration by parts. Okay, that was 9.1. Then after that, we did some fractions. So that was like long division and partial fraction decomposition. Really, I probably should have shown you long division during calculus AB, but I knew that all of you would be back with me this semester, so I knew that that one could wait. Then after that, we did some improper integrals last time, and that was good. Helped us review our techniques, but also, really focus on how we justified our answer. And then today we are going to integrate after completing the square. But it's kind of like, what does that even mean? That has got to be one of the more obscure topics in AP Calculus. And because it's probably been a while, I'll just take a couple steps back to Algebra 2 and remind you what we even mean by completing the square. Complete the square to rewrite the quadratic expression in the form a times x minus h squared plus k. Alright, so we got this x squared plus 12x plus 37. What we really do is we take the x squared plus 12x, and that's going to stay the same. We're going to divide the 12 in half and get positive 6, and then we're going to square that and we'll get 36. And what we typically did in Algebra 2 is we either added that number to both sides of the equation or added it and then subtracted it, right? Because we're trying to add a clever form of 0, and then we still have that 37. Now, for me, at this point, knowing what you know now, I think you'd be fine to just write plus 36 plus 1, because you're going to see that we're eventually going to combine that negative 36 and the plus 37 to be a 1, but, that's totally up to you. So then what we kind of did was I realized that, by adding that 36, we had completed a perfect square. We'd made a perfect square. So the thing inside the blue parentheses was x plus 6 times x plus 6, and we rewrote that x plus 6 squared plus 1. So then on the right, if I had t squared minus 3t, these could be a little bit more annoying, right? We'd divide that negative 3 in half and get negative 3 halves, square that, and so I would need to add 9 fourths to complete the square, but to make sure I wasn't actually changing the expression, I'd need to go ahead and subtract that as well. And then we'd realize that, okay, the first 3 terms made t minus 3 halves squared, and then we're subtracting 9 fourths. Okay, and that's all great, but that's not even really all that helpful for what we need to do in calculus. But before I even get to the calculus, I do feel obligated to complete the square on one of these and show you that this is really not as bad as it seemed 2 years ago when you were in my Algebra 2 class. Remember, these caused us a lot of problems. But what we're going to do here is we're going to factor out the 2 from the t squared and the negative 8t, but not the 9. Okay, so we're going to say that this is 2 times t squared minus 4t plus something, and then I'm going to still have that plus 9. I can't be losing that. But I just need to be careful that I'm not adding like anything but 0 to this expression. So what would I add on the inside of the parentheses to make that a perfect square? T squared minus 4t, negative 4 divided by 2 is negative 2, square that, that's adding 4. But if you just look at this, you can see that I've not just added 4, but 2 times 4, so I need to subtract 8 to be fair. Like if I was to distribute the 2 back over all that stuff, I need to have plus 8 minus 8, and then plus 9 over there. So I would have 2 times t minus 2 squared plus 1. That's all I have to say about actual algebra complete square. Okay, so the trick with these is less actually executing the technique than recognizing when to use it. Okay, so that's where you're going to see, and this homework set, and even in these notes, you're going to see a bunch that kind of look the same, have slight differences, and those are going to really change the way we integrate. That's kind of the key here. So the first one on the far left, I'm looking at the denominator, x squared minus 10x plus 16. It's like, I can factor that. That's x minus 8 times x minus 2. And if I can factor the denominator, then I'm going to split up that fraction using partial fraction decomposition. Okay, but we did that 2 lessons ago, and y'all were pretty good at that. This year especially, and I'm sure that in the future y'all are going to also be really good at this technique because it's so algebraic and it works the same way every time, and it really leverages what you're already good at coming into this class. So I'm not going to take this one any farther besides to say you do the a and the b on it, partial fractions, y'all know what to do there. The one in the middle, 1 over x squared minus 10x plus 25, I can also factor, but this one is a perfect square. This is x minus 5, x minus 5. And so, like, at this point, I'm just going to say, well, you should just write that as x minus 5 squared. And this one is actually not one that we're supposed to do partial fractions on in AP Calculus because we're supposed to do that on linear, non-repeating factors only. But x minus 5 squared is a repeated factor. But fortunately for us, there's an easier, faster way. We're going to say, wait a second, this is x minus 5 to the negative 2 power. I can apply the power rule to that, add 1 to the power, divide by the new power. I have negative 1 over x minus 5 plus c. Okay, this one's nice. Okay, but the one on the right is very similar to that one, but it's just bigger by 1 in the denominator. So that's what I'm noticing. Okay, the denominator is bigger by 1. So maybe I'll just kind of like write it exactly like I had attacked the other one. I'd say 1 over x minus 5 squared plus 1 in the denominator, dx. It's like, okay. And, you know, and always when I write this on the screen, I get a few people that recognize, okay, oh, I know what I'm going to do with that. Okay, but if you don't see what's going on, I'm going to do a little u substitution. This is not going to be a very interesting one. I'm going to say u equals x minus 5, du equals dx. And this might help you a little bit. I might say 1 over the square, or 1 over u squared plus 1 du. Okay, and if you don't see it from there, the only other thing I can really do to try to help is 1 over 1 plus u squared du, that antiderivative. And this is one that we're just supposed to recognize. We have to know this one. We know that this is the derivative of arctangent of u. So we're going to say that this antiderivative is arctangent of x minus 5 plus c. Okay, so the key reminder I've got for you is that the derivative of arctangent of a thing is 1 over 1 plus that thing squared times the derivative of that thing. Okay, we're going to need that one, and we're going to also need the one for arcsine. But before we get to arcsine, I want to talk a little bit more about arctangent and do another example. So I want to remind you about a couple of key facts about arctangent, which is really what we're going to need to know for AP Calculus. So I'm going to kind of draw a little trig diagram here and say, first thing is, what do we do when we get arctangent of 0? Okay, we think to ourselves, where on the unit circle is tangent theta most obviously equal to 0? And I think that would be right over there, and that's theta equals 0. So we say that arctangent of 0 equals 0. And the second one is arctangent of 1. Do the same thing. Ask myself, where on the unit circle is tangent theta most obviously equal to 1? And I think that would be right up there. Okay, and that would be at theta equals pi over 4. So that means that arctangent of 1 is pi over 4. And then the last one is the fact that the limit as x approaches infinity of arctangent x is equal to pi over 2. And that's kind of like saying where on the unit circle is tangent theta most obviously approaching infinity, and that would be up there where I'm getting sine over cosine going towards 1 over 0. So that if I was confronted with a definite integral like this one here, you would be able to actually find the value, and especially in a multiple choice setting, get the correct answer. So the integral from 4 to 5 of 8 over t squared minus 8t plus 17, this one is also one bigger than a perfect square. T squared minus 8t plus 16 is the square of t minus 4. So I'm going to say this is the integral from 4 to 5. 4 to 5 of 8 over t minus 4 squared plus 1 dt, and that antiderivative is going to be 8 arctangent of t minus 4, and I'm going to let t go from 4 to 5. When I plug in t equals 5, I would get 8 times arctangent 1, and then I would subtract, when I plug in t equals 4, I'd have 8 arctangent of 0, so that'll equal 8 times arctangent of 1 is pi over 4, minus 8 times arctangent of 0 is 0, so 8 pi over 4 is going to be 2 pi. So now, like I said earlier, we're going to need to also think about integrals that come back and are related to arcsine. So I need to remind you of the derivative of arcsine. Okay, so if we take the derivative of arcsine of a thing, that's 1 over the square root of 1 minus that thing squared times the derivative of that thing for the chain rule. Okay, and notice that only one of these is really going to fit into that pattern. It's going to be the third one, right? Because the others aren't exactly that. It's not 1 over the square root of something minus something squared. Okay, so with the first one, we're just going to be using power rule. Okay, so we're going to rewrite the square root of 36 minus x as 36 minus x to the half power. I guess I did that mentally and then just went straight for the antiderivative, right? So it's to be 2/3 of 36 minus x to the 3/2, and I need to divide by -1 to prepare for the chain rule. And I'm going to let x go from 0 to 6. And so when x is 6, I have 36 minus 6 is 30. So -2/3 of 30 to the 3/2 minus -2/3 of 36 to the 3/2. We'll say we could probably figure that out because it'd be 6 to the 3rd, which I think is 2/16, but it's just not going to be something we want to take 2/3 of because we can't take 30 to the 3/2 power. So that's going to be as far as I'm going to take that one. The one in the middle, we need to be able to recognize that that integrand, that square root of 36 minus x squared in the numerator. Okay, we need to know what the graph of that looks like. You know what y equals the square root of a squared minus x squared looks like. I'm trying to give you the hints. We need to use geometry for this one. Okay, so this is going to make a circle centered at the origin, the upper half of a circle is centered at the origin, radius 6. And so if I'm integrating from 0 to 6, that's going to be that portion of the circle. That's a quarter circle, so the area is going to be a quarter of pi times the radius squared, so 36 pi divided by 4 is 9 pi. And then this third one, that's the one that's going to require us to complete the square. But it doesn't really look like I showed you at the beginning us completing the square like we did in Algebra 2. Neither did the ones with arctangent. So I see how it is that it relates, but I can't figure out how to show you algebraically how it's the same thing. So I'm going to show you what we are going to do. We're going to take the 36 and we're going to factor it out inside the square root. That's going to be our first step. So I'm going to have 1 over the square root of 36 factored out from 1 minus x squared over 36. Okay, and then I'm going to kind of apply a radical property. That's going to be 1 over the square root of 36 times 1 over the square root of the thing in parentheses. So I'm going to have 1 over the square root of 36 times 1 over the square root of 1 minus x squared over 36 dx. But I would be wise to write x squared over 36 as the square of something, and I can do that. That's the square of x divided by 6. Okay, so I'm going to have that here, and I'll say, all right, 1 minus x divided by 6 squared. Okay, this is all looking good, and now I'm going to kind of rewrite again and set up for a u substitution, just so I can show you all the steps, because the thing with the 6's here is it's very subtle. So I'm going to go over and I'm going to say, all right, the 1 over the square root of 36, I'm going to factor that out the front of the integral. So I'm going to say, but I guess first I'm going to tell you, okay, u equals x divided by 6, du is 1/6 of dx, get that so you can see it, and that means that 6 du equals 1 dx. Okay. So now I'm going to factor out the 1 over the square root of 36 and write that as 1/6. And I'm going to be integrating 1 over the square root of 1 minus, okay, I'm going to call that u squared. And then 1 dx is going to be 6 du. And so I'll just put that off to the side like that. Okay, now the 1/6 and the 6 from the 6 du, those are canceling. And so I'm left with the integral of 1 over the square root of 1 minus u squared du, which is just arc sine of u plus c. And we said that u was equal to x over 6, so this one is 1 arc sine of x divided by 6 plus c. But if I go off to the side and check using the derivative, you can see how it works, right? That 1/6 that comes for the chain rule, that's the 1 over the square root of 36 that I could distribute back in to make 36 minus x squared in the denominator of that inside the square root. Okay, so that one's a very specific thing to happen, and you'll get some more practice on that on the homework. But if you just do this a couple times, you'll understand the algebra, and it will be no big deal. Okay, now going back to arctangent, we can have kind of the same thing happen there. And that would be if we were looking at 1 over this, or 1 over not the square root of x squared plus 36, right? Just regular x squared plus a square number in the denominator. And we're going to deal with that largely the same way. We're going to factor out the 36. So in the denominator, I'd have 36 multiplied by 1 plus x squared over 36. And maybe you see the same thing coming, and it's going to work the exact same way. I'm going to factor out the 1 over 36, and then I'm going to write the x squared divided by 36 as the square of something. Now this time, I don't think you need me to go off to the side and write a u substitution, right? It's going to be 1/36 of the arctangent of the thing in parentheses. I just have to be careful for the chain rule, right? Because the chain rule is going to bring out a 1/6. I need to prepare for that by multiplying by 6. So that's where I'm going to have 1/36 of 6 arctangent of x over 6 plus c. And then I'm going to say, all right, that's equal to 1/6 of the arctangent of 1/6 of x plus c. And if I go off to the side and check again, I'll see that I actually do need that 1/6 to make sure that I have, kind of 2 powers of it out to the side, and I get the 1/36, so it works just right. Okay, so that's kind of how it's going to work in the arctangent case. And now before I let you go, I got a couple more. So I've got this 3 over 2x squared minus 28x plus 100 dx. It's like, what are we going to do with this? And but you notice that all the factors of all the pieces of the denominator are even numbers. So I could factor out a 2 from that. So I'm going to factor a 3 out of the numerator and a 2 out of the denominator. And see, I'm left with 1 over x squared minus 14x plus 50 dx. So if I tried to factor that, maybe do partial fractions or something, and be like, it's not quite right. It looks like a typo. And it's 1 bigger than a perfect square also, so this one's going to be arctangent. Okay, x squared minus 14x plus 50 is 1 bigger than x squared minus 14x plus 49, which would be x minus 7 squared. So this one's going to be 3/2 of arctangent of x minus 7 plus c. Alright, and now the last integral I've got for you, I kind of forgot to put one of these in here, but that I always like to include with ones like this, is the one that you can see kind of in the middle of your screen. Integral from 3 to 4 of 2x divided by a squared to 25 minus x squared dx. And this one, it kind of has, it looks like it's got that element of arc sine to it, but it doesn't. Right, it's missing that piece. That 1 over that 2x is just like not helping us on our pursuit of finding this antiderivative. So what we need to do is use a u substitution. And if you're curious on how that goes, you should probably pause the video and try to work it out yourself, because you're at the point where you should be able to do this one without too much difficulty. But if you use u equals 25 minus x squared, you should be able to get yourself an answer. Here's the work, but I think that now pretty well covers it as far as integrals that have this pattern with a square number and a squared x. That is kind of what I would say. So that's going to be all for this video. Thanks for watching.